Hello, am I audible properly?
Yes, sir.
Okay, fine. So we will wait for a couple of more minutes and then we will start. So, hey Murli, meanwhile everyone will join. Can you introduce yourself in brief?
Yes, sir. I'm Murli, pursuing MTech in Structural Engineering from UEC.
Okay, so where
Yes,
like
sir. I'm from Karnataka.
okay, nice. So I think I mean you have written this last question out of second assignment.
Yes, sir. Yes, sir.
Yeah, I also thought that as a correct option B, but like we do not have access to edit the answer sheet, so I kept silence on that. Yeah, but
Yes, sir.
now afterward, like if you have any doubts, like please bring that during the sessions. We will discuss that.
Yes, sir. Sure.
Sure, sure. So I think now we will start. I will share my screen. So are you able to see my screen?
Yes, sir.
Okay, fine. So what we are going to do today is like we are going to discuss about basics of remote sensing. So in the last week, we learned about like what is remote sensing, its advantages, disadvantages, and further how a typical remote sensing system will look like. So various component of it, such as the source of energy, let's say if it is sun or the satellite itself, then the medium through which it is coming to the earth, which is our atmosphere, then it is interacting with the object at the surface, and then reflection, either reflection or emittance will happen. Basically, reflection, absorption, and scattering will happen. These three different mechanism, and then it will bounce back towards the satellite. So it will go through the atmosphere one more time, and then it will be recorded by the satellite. Then it will send that to the further processing purpose to the downstream stations, and then it will like we will process those data and publish in terms of applications or in terms of map. So this is a typical remote sensing system which will look like. Now, if we see like whenever we capture something through remote sensing or satellite or drone or aircraft, how the output will look like. It is similar to something like this. So the first thing is like in the last class we discussed is that remote sensing is a science as well as art. Science, it means like how to design the satellite in such a way that it captures a different essence of the various phenomena or the objects which are there on the earth. And the science in terms means once you get all those images, how to interpret those images, which involves the art part. So here, like we will start today's lecture with this particular imagery. So can any one of you will say like what kind of objects can you identify any type of objects or phenomena from this particular image? So Abir or Murli, can you just say like what kind of thing that you can see from this image?
Sir, I think from my side, due to network issue, I'm unable to see that slide.
Okay. So is it loading in your screen, Abir?
Yes, it is visible to me, and
Okay.
I'm also. I think I'm the first slide is only visible to me. Is it the
Okay.
first slide, or are you showing
The one
another?
with the image. So are you able to see my screen properly?
Yes, sir.
Okay, now I will present one more time. Just give me. Are you able to see any image on my screen?
No, sir. They are only echoing image there.
And just do one more time. Are you able to see it right now?
Yes, sir. It's now pretty much visible.
Okay, so now can any one of you tell me like what are the objects or phenomena that you can see here?
Yes, sir. Actually, I'm expecting a coastal city here.
Yes,
There's the
that is
sea
of
level
course
were matched with the
images from coastal area.
yes, sir. And there are some vegetation are there, and the white, the deepness of the sea is very low. So it's
Hmm.
actually the starting point of the sea, and there are a lot of houses and are roads, and the vegetation, and especially the land is plain.
Yes, exactly. So it's there is no hill or any other type of features present in this particular image. Okay, and in vegetation also, are you able to differentiate different types of
Sir, you
vegetation?
are not clearly audible.
Yes.
Sir, you are not clearly audible.
Okay. Am I audible? Hello.
Not clear at all, sir.
Am I audible?
Yes, sir.
Okay, so I mean now if you see the different vegetation, so do you see different types of tree in this image? Like, are you able to differentiate trees as well? Uh, Hello. So are you able to differentiate any vegetations as well? Hello.
Sir, your voice is coming echoing, not properly.
Okay, okay. Just let me change my image. Just give me a sec. તમારા કોઈ ફોનમાં નેટવર્ક આવે છે તો મને કહો ને. હા. હેલો. Hello. Am I audible now? Okay, so I will try to share my screen with another device. Actually, I'm not having good connection today. So let me share my screen one more time. Hello. Uh, am I audible now and my screen is visible? Okay. So now I think what I was asking is, let's say if you take this example, so in this, are you able to differentiate between the different types of tree or not? Uh, okay, let me share it one more time. Is my screen visible or is not showing anything? Sure. So when I'm showing this image, so my question is, are you able to differentiate between trees and different types of tree basically in this given image? Yes. Oh, okay, fine. Now, like, what is the parameter that you have used, I mean, to differentiate the different objects? Like, what tells you that it is a tree or it is a water? So by looking at which typical thing you are saying that this is water or this is exactly. So the thing is color. So first thing, like whenever we look at yes. So the first thing is color, elevation, exactly. Then the next thing, I mean, if you want to differentiate between this, like let's say there are different houses. Okay, so if you want to differentiate between different houses, then what is the parameter that you will see? Locations, and then we will see also the size and shape as well. So if solar panels are mounted on the roof or not, so how will we find out that it will be having in rectangular shape, then black in color? If roof is normal, then there is nothing. So we will see the different aspects of different objects or the phenomena. So the first thing whenever we see any picture, we will see the different tones and colors. So how the intensity of the images which we have captured, that is changing. So basically each image is a reflectance value. So how that reflectance is changing, which object is reflecting more and which object is reflecting less. That first of all we will find out. So that is according to tone and depending on tone and colors. So what if the reflected energy is high, then it will show a white color. If it is less, then it will nothing. So black color. Similar to that, like now if we see go, this is the basically primary principle to differentiate any object. Then if we go to the secondary thing which classify the different object is depending on their size. So here in this image, if I see like what are the different types of tree that you can identify. So here in terms of tree, you can see near the coastal line, there is a different types of tree, which is like coconut tree or something related to that. So how we can see that the canopy is very less there. So the shape is different. The tree which are there on the roadway and the trees which are there on the coastal area both are having different properties, different canopies, different height. So their size is different, shape is different, and according to that we can also differentiate between two different same classes as well. Then texture also. So texture, it means that how the intensity is varying, is it the smooth or is it different. So if you see over here, whenever like where my cursor is, so are you able to see my cursor over here? Okay, so see, there is some grass is presented there. So you can see the smoothness is kindly similar. And if you see over here, some forested area or so many trees are there. So you can see it is like texture is like trees are not in the some like similar way. Like each tree is not having same height. They are having different canopies, different types, and because of that, it has little bit like friction, or you can see this like rough in nature. Whereas you can see this grass which is very smooth. So that is termed as a texture, which we can also refer to differentiate between different objects. Then the third type of a parameter that we can use at third level, it is the different types of pattern, height, and shadow. So height, which we have used for to differentiate between this coconut tree and these normal trees which were present. Similarly, you can see the shadow on this particular street, shadow of the trees. So that will be like we are using the height parameter. Pattern, it means this how these houses are arranged. Here you can see these are the, you can see like in between you can see one line. So this is showing that there is some slope is there. Here, if you see on top, this is just a flat surface over here at the below center. So you can see that there is nothing like a slope roof. So roof is like flatted roof, or it is a RCC roof, or some kind of similar material is there. And the other houses, if you see in this area as well, they are having this four-dimensional roof. So like it is having the four different panels on top of the roof. So that kind of information you can collect depending on the different patterns. You observe some patterns, or you see the shadows and height, or else you can just see the different heights or as well. Like so, after that, the site and association. So, how do you get to know that this is a coastal image? Because one side of the image is like having just water, and then why coastal only? Why not lake or something else? Because if water is there, then there might be it might be a lake also. So why just coastal area? So can anyone say like why did you imagine it as a coastal area, not the river or not the lake or any other type of water body? Yes, exactly. Yes, and secondly, you can see there is a sand which you can see near the like shore area, and then this kind of tree can be found out like coconut trees on the seashore only most of the time. And these are the some patterns. You can see some swimming pools, so you can see some villas are there, which is giving the sea view. So what you are doing is you are associating the different features which are present on the seashore, and that then you are saying that this is a shore or something else. So depending on the features which are present in the image, you will try to like collect your information which you learned till now in your brain. You will process, and then you will see the association with of each and every object, and then after based on that association you will say something about the particular image. So that we are seeing it as a association and the site, so where it is located. So like whenever we want to do visual image interpretation, first these are the basic principle, that the first criteria which we will use is the tone or different colors. Then as a secondary criteria, like we will increase the degree of complexity of interpreting the visual image. Then it will we can use the size, shape, and texture. Further, as a tertiary criteria, we can use pattern, height, and shadow. And then as further different sites and their association with the nearby feature. Now you have heard about this word resolutions in the this week's recorded sessions, that like we have our characteristic, every image which we are capturing through the satellites, they are also having their characteristics, which is known termed as a resolutions. And there are four types of resolutions which are present in the remote sensing dataset. The first resolution is the spatial resolution. And here the spatial resolution means that how we can zoom or identify any particular object. So here, let's say if I give you an example that some house is there and you want to see that house, let's say Taj Mahal. Taj Mahal is there and you want to see the Taj Mahal through satellite. So what will happen, like if we keep our satellite too high, like the altitude of the satellite, if it is too much, then we will see that entire Taj Mahal is just one pixel. It will just create very coarser resolution image. And as we go down, it will like details will become finer and finer, and then we will able to resolve the Taj Mahal properly. So like whether we are able to resolve any given feature or not, any farm or not, any lake or not. So that is termed as a spatial resolution. So whether you are able to differentiate any object which you are interested or not. So if I am interested in monitoring the water bodies, so am I able to monitor each and every water body present in my district or in my state or not? So here you can see one example of detection of paddy field. So the rice field we want to detect through the remote sensing. So the first thing, am I able to detect the entire field or not? So here you can see this first imagery is having the resolution of 6.5 meter. It means each pixel in an image is representing 6.5 by 6.5 meter area. So you can see you can differentiate the different paddy fields properly. So red and yellow you can see here. Now if we increase the resolution from 6.5 to 13. So what we are doing is we are doubling the resolution. So 6.5 to 13. So like it will become more coarse. Now one pixel will have the dimension of 13 meter by 13 meter. So what we have done is like we have reduced the pixels by how many times? So earlier it was 6.5, but now we made it to 13 meter. So how many times we reduce the pixels? 4 times, exactly. So earlier it was 6.5. Now what will happen if we want to make it 13? We will combine the 4 pixel of 6.45 meter like in each side. So it will become a 1 pixel of 13 meter. Similarly, from 13 to 60, 26 if we go, then it will be like 6.5 into 4. So 4 into 4, 16 times. Okay, so similar to that, like in the power of 2, like we are increasing the number of like the pixel. So if you just see, as we are going to the resolution is becoming like coarser. So you can see 6.5 to if we are going towards the 208 meter, we are not able to detect different paddy fields. So you can see till 26 meter, the paddy fields are quietly monitorable. After that, as we go from 26 to 52, the response of the nearby features is mixing with the paddy field. So you can see over here. So now this red line is the actual line, it's a line from this image, and this black one is the original line of the paddy field. So now you can see this black thing like till as we are increasing the resolution is becoming coarse, you are not able to distinguish between the paddy field. So till 13 meter it is quite okay, but 26 also it is giving pretty like moderately good result. But now when we go towards the 52 meter, now you can see this red and yellow line. These are the paddy field detected by the satellite, whereas the black one is the original one. So you can see the very high deviation between these two. So are you able to see these small details, or should I zoom it or something? Uh, are you able to see this detail? I will try to zoom it. So now, are you able to see it properly? Compared to previous. So now you can realize that now as we are going from 6.5 meter to 208 meter, that how the accuracy is diminishing for detection of the paddy field. So the earlier, like what we are doing is, if we are going from 208 to 104 meter, so here you can see this is just one single pixel. Now that single pixel is divided between four different pixels, because what we are doing is we are making the dimension of that pixel by half. So we are increasing the resolution by 2 times, and it will increase the number of pixels by 4 times, because in every dimension it will divide the side into two sides, so 2 times 2, so it will become 4. So if we reduce the increase the spatial resolution from 208 meter from to 104 meter, then the number of pixels will like become from 1 to 4. And now when I'm talk about increasing the spatial resolution, it means that I am reducing the size of the pixel. I'm growing from 208 meter from 104 meter. It's not like increasing spatial resolution means increasing the size of the pixels. Okay, so basically the main definition of spatial resolution is how good you can resolve the object. So if the pixel dimension will be less, then and then you can resolve more. So if you want more details, your pixel size should be minimum, or it should go near to 1 or it's a centimeter level, depending on what kind of object you want to detect. So here for rise field, if we talk about, so from 208 from 104, if we increase the spatial resolution by 2 times, the pixel number will become 4 times. And then if we go further down, so it will become the 4, 4, 4 and 4. So each box now will be divided into 4 different boxes. So it will become 16 pixels and 52 meter resolution. Then if we go further down, then 16 into 4. So 64 pixels it will become, and then similarly it will go on, and it will increase the number of pixels and increase the spatial resolution, and we can differentiate, like detect the objects well. Now this is the another example through the whatever the data which is available in the through the satellite. So there are three different satellites. One is the QuickBird, then the another satellite is the Landsat, and then the third satellite is the Modi satellite. So you can see here this QuickBird satellite is having the resolution of 2.4 meter. Then Landsat is having the resolution of 30 meter, and Modis is having the 250 meter pixel resolution. So first of all, if I ask you the question that which of the satellite is having the highest spatial resolution, so what will be your call on that? Yes, so you can see more finer details, and which one the satellite sensor is having coarser resolution, then it is a MODIS, which is representing 250 meter. Now we can see this is a one coastal image which we see just earlier. So like if we want to represent coastal line or something, if we want to study coastal line, then you can see the QuickBird is still good, but if you take MODIS, you are not able to differentiate between the coastal line and the surrounding land area. It's very difficult to distinguish between the coastline or to delineate a coastline. So this is the problem with the this coastal resolution. So depending on what kind of thing you want to do. Suppose if I want to see what is the vegetation condition or the forest condition or the overall greenness over entire India, I will go for MODIS, because in that case I do not need to see at what is happening at 10 meter or 5 meter or at say 30 meter. So if I'm doing a scale at country level, it's MODIS is good. 250 meter is quite good resolution. In the same fashion, like if I want to see what is happening with the vegetation in one of the sub district, let's say, so what is happening in the Gandhinagar sub district or Gandhinagar district. So in that case, I'm looking at very sub district level scale or district scale. So I need very high resolution. For that, I can go with the Sentinel satellite, which is having 10 meter spatial resolution. So if I'm going working with the state level, then Landsat will also work good because it is giving images at 30 meter. So depending on what you are doing and at which level you are doing, it will define all your resolution, that which resolution to use for which kind of application, that we will see further after learning all the type of resolutions. So here you can see, if we are taking then this is the another disadvantage of the increasing. So what will happen if we increase the spatial resolution? So you can see here, if we have this uh, like quick bird satellite, then the area which we will get is very less, which we will get just 15 you can see, if just we'll get in at a time, we will get an area of 15 kilometer by 15 kilometer only, which will give us the only local information. But if we see these Modi's satellite, then we can see little bit more area, which will cover like 50-kilometer area as well, which you can see over here. But similarly, if we go for the Modis, then we can, at a single time, we can see very big chunk of a land we can collect in just one go, one image, which is like around 1,000 kilometers. So there is a trade-off between like how much area you want to cover in a one go. So if you want to cover a larger area, go for a Modis. If you want to cover a very small area, then go for a satellite like Sentinel or QuickBird, which are having very high spatial resolution. So depending on that, we can like our application, we can specify the spatial resolution. Now the second term or second types of resolutions which is there in the remote sensing is a temporal resolution. So temporal resolution means that at which frequency satellite is taking the images of any particular area. So let's say we have one satellite which has collected the data at June 1st of 2006. Now the second image of the same area will be acquired after 16 days, because orbits are designed in such a way that it means like it cannot cover entire area at once. So we have to divide our entire earth into just different parts or segments, and then it will cover the different parts of the world. So same portion it will cover after 16 days. And similarly, now if I want to study something like cyclones or floods, will it be helpful to us if the satellite has a resolution of 16 days? Will it be good to use it for cyclone application or flood application or landslide application? It's not good, exactly. Why? Because most of the time when flood will happen, the water will go down, or the all the works they have already did in the 16 days or in a week only. So the next image we will get, which is after 16 days. So this resolution is not good. So if we are analyzing floods, at least we need the images after just 3 or 4 days. At least one image if I getting on June 1st, the second image should be on June 3rd or June 5th, depending on the satellites which are available readily or publicly. So we have to see, if we're working for flood application or cyclone applications, we have to select satellites which will give us like maximum temporal resolution. So now if I tell you that you have to monitor the forest area of the India, for that, will it be good to use 16-day resolution or not? Yes. Why? Because forest greenness will not change drastically. If any kind of deforestation is also happened in between the forest, it will take time to reflect that on the larger scales or in the field. So, like small scale phenomena, if we want to do small scale in terms of size as well as in time, the temporal resolution should be high. But when we talk about the something like deforestation or the drought, so for that we need something like 1 month, or if we just get one image, like we want to study drought, then if we have just one image at 16 day or one image at 1 month, then also it will be fine for us. So basically this higher temporal resolution means more frequent updates, which will help us to monitor something like where do we need high temporal coverage. It means whenever we are like interested in monitoring crops, because it will change directly from the sowing phase to the plantation sowing, and then it will become big. So it will like this different types of stage will cover in this few weeks only. So for that, we need higher temporal resolution. Instead of, if we want to see the urban development, we do not need that much high resolution, because one building, if you are considering, then it will take 6 to 8 months to construct. So if we have annual images also, so if some satellite is there which will give us the annual products, then also it is good for us if we are looking at the urban development. So now we will see the third term or third type of resolution, which is known as a radiometric resolution. So this radiometric resolution, it refers the sensitivity of the particular object. So let's say some light is reflecting with the object and it is coming back to the satellite. So how to differentiate between two different let's say leaf. If we have two different leaves, then how to differentiate both of them? So let's say one leaf is there which is reflecting more, and one leaf is there which is reflecting less. So we can differentiate in if let's say reflectance, if we say that reflectance for one leaf is 50 and reflectance for one leaf is, let's say, 10 or 20. So we can differentiate, one is 20, one is 50, we can differentiate it easily. But if the difference is very less, that one leaf reflectance is 50 and then the another one is just 45, then it will become quite difficult to differentiate between these two leaves. So basically we will sense the energy from the different object, but how to represent that energy as a visual format? So generally when we put something in an image, we will take a very simple example, that if we have just single image, we can represent it as a black and white image, either 0, either 1. If it is reflecting, then 1. If it is not reflecting, then 0. Okay. Now if I say, now if we take few more bits, let's say 2 raised to 2. So it will present 4 different values, as you can see here. So in that, along with the white and black, we have two shades of gray, which will help us to increase the sensitivity. Now, if we take a scale from 0 to 100, then 0 to 25 will be like a black, then 25 to 50 will be this darker gray, then the 100 and 1 to 150 will become the lighter gray, and 150 to 200 will become white. So like that, like we can represent, like we have the color range from 0 to 255. So when we talk about that in like paint or in PowerPoint, when you are making PPT, you see the colors as a range of 0 to 255. So it means they are representing the 8 bits. So variations of color we are representing as a 8 bit, which means this 2 raised to 8, which will make 0 to 255. Now, if we increase the number of bit, it can sense the different things differently. If two similar leaves are also there, then okay, audible. I'm not that audible. Okay, so hello, am I audible now? Okay, so I will repeat it this one more time. That now in our screen, when we see colors in paint or PowerPoint, you can see this range of 0 to 255 when selecting any colors. If 255, 255, 255 is there, then it's white. If 000 is there, then it's a black color. So if it is reflecting everything in red, green and blue, it means it is a white color. If it is not reflecting anything, 000 in RGB window, then it is termed as a black color. So depending, if we increase the number of bits, then it will be increase the different, like we can represent the different objects as a different shades, which will help us to differentiate between different features as well. So here you can see in the first image, you can see the color as a here you can see this color is a just black color only, so it is not reflecting this. Every value is concentrated between this twin, but now we have divided this into different 4 shades also. So yeah, you can see now just only middle part is black, the nearby feature it has converted into gray. So only this some pixels are there, they are having proper black value, others are having gray color. So like that we will see the different sensitivity of different objects, and then we will present in terms of beats. So when we talk about this satellite data which we are acquiring, so this Landsat satellite, if you have heard of, that is having the 16-bit radiometric resolution. Some of the satellite also have 24-bit resolutions. So we will see those things with the real life data set afterward. Now the next resolution is the spectral resolution. So spectral resolution is, we have heard about, like learned about this electromagnetic spectrum in the last class. So how much portion of the electromagnetic spectrum we are extracting, or how much information from this electromagnetic spectrum we are getting, that is termed as a spectral resolution. So whenever we want to detect something, what we will do, first we will keep particular object into laboratory under spectroradiometer, and then we will measure that how that, like object will respond into different wavelength. If we keep leaf, then it will reflect more in the green color compared to blue and red. So we can say that it has more reflectance in the green window. But what about the different wavelengths which are present in the EM spectrum, like infrared, microwave, radio? So we will put each and every light on the leaf, and then measure the we will measure the response which we are getting back from the leaf, and then we will generate one curve which is known as a spectral reflectance curve. Now how many bands we are presenting in the satellite data, that is your spectral resolution. So here you can see this is like green window one band, R window one band, near infrared window one band, and near infrared this is band number 4. So here we are using 4 bands. Then you can see this is the image how it will look like in the blue band. It means the energy from blue band, it means this 0.4 to 0.5. So 0.4 micron to 0.5 micron is going to this object, and whatever is coming back, that is recorded by the satellite. Now energy from this 525 to 0.05 nanometer wavelength band is going towards the object, and it is coming back to the satellite, and that is whatever the information is given by the green band, that is shown here. Similarly, what is the reflectance in the red band, and what is the reflectance in the near infrared band. Now you can see if we are going from this blue band to near infrared band, can you notice that one thing is happening if you are going from blue band to near infrared? So what is your observation from this? Like if we are going from blue band to near infrared band, what is happening in the image? You can focus on the corner parts, let's say parts which are over here. So what is happening with this particular portion? So if you compare all these 4 images, so this is the response from the blue band, this is the response from the green band, this is from red band, and this is from near infrared band. So if you see the response from each and every band, like what is the change that you are seeing as you are going towards the near infrared band? What? So can you see the first objective which we like learned during visual image interpretation is tone or color. Okay, so is color is changing? Yes. So how it is changing from black to white or white to black? White to black. So if you go from blue to near infrared, top to down, then it is becoming black to white. So it means if we are increasing the wavelength, we are going from 450 nanometer to 750 nanometer, or when we talk about this wavelength in this way, or in terms of electromagnetic spectrum. So when we talk about this electromagnetic spectrum, what we are doing is we are going from uh, just a minute. We are going from the wavelength from blue to near infrared. So we are going towards the longer wavelength, and like vegetations will reflect more in this particular windows, near infrared window. And whenever we see something white, it means that they are reflecting more, and black, it means it is reflecting less. So it means that whatever the objects which are looking like black color, that are not reflecting that much, but colors with white and the like lighter gray color, they are reflecting more energy. So basically, which portion of the electromagnetic spectrum which we are covering, depending on that, it will say like what is the spectral resolution. So some satellites we will consider just 4 to 5 bands, but in some satellites we will consider the different bands. Like here, if we put 3 bands in visible, 2 or 3 bands in near infrared, 5 bands in microwave, or something like that. So if number of bands are too much, then it is termed as a hyperspectral remote sensing, where you are putting your band in each and every wavelength. If you are just having a single band, then it is considered as a monochromatic image, or image with just one band. If you are having multiple band, which is ranging from 5 to 6, then it is considered as a multispectral remote sensing. So these are the classification of remote sensing depending on the how many number of bands they are using. In number of bands here, it means 3 bands in visible light, 4 bands in infrared, 3 bands in microwave, so on and so forth. So how we are dividing each and every wavelength region. Now, when we talk about different applications, so let's say first application is forest cover mapping. So for that, if we want to see how these 4 characteristics we can use, so spatial resolution for forest, it means we need very high, not very high, like we do not need 1 meter or centimeter scale accuracy, because trees, if we are taking forest, there are different bunch of big trees, and the forest area is quite large. So we can use the spatial resolution from 30 meter to 100 meter, and time is also 1 year to 2 years. Then if we take forest fire, then we need very high resolution to find out the patches which affected due to the forest. So both are related to forest, but one is forest cover mapping and the second one is a forest fire. So when we talk about fire, it means it's a rapid phenomena. So we need very high temporal resolution, which will be like 12 hours to 2 days as well. And then the spatial resolution also should be high, or it's like 30 to 500 meter can also be enough, because we directly see the black patches. Depending on the size of the forest, we can identify that how much area got burnt. So basically go for 30 meter. Apart from that, if you are having forest area very large, then you can go till 500 meters as well. Then if you want to monitor temperature or precipitation, so these are the formula, like these are the phenomena, like it will not change drastically, like temperature will change hourly as well. So we need 30-minute to 1 hour scale in terms of temporal resolution, where in terms of temperature it will not change a lot with this partial variability. So we can go for 1 to 8 kilometer as well. But if we have sudden contrast in the different landscapes, let's say urban landscape is there or vegetation is there, which is changing drastically, like just near to the urban area, just one forest is there, then it will regulate the temperature. So in that case, we need high spatial resolution. But in general, this phenomena will not vary spatially that much. So we can go with the 1 to 8 meter scale, kilometer scale as well in the terms of spatial resolution. Then precipitation, we can go with the 4 kilometer variability in spatial dimension, and like in small time it can rain heavily as well. So we need a temporal resolution of 10 to 30 minutes. Now if we see the land use land cover classification. So land use, it means we will take each and every pixel and we will classify it as a, whether it is urban land, agriculture land, forest land, water body, waste land. So it depends on different types of level, at which level we want to classify our image. And this thing will change, not change daily or monthly or annually. So we need, like if we are looking at very coastal resolution or the like India level scale, then we can take a data from 5 to 10 years as well. Every 5 years we can publish a map. If we are seeing a state level, then we can do it within the 3 to 5 years as well. And if some sensitive areas are there, that smart city is there, or let's say Dholera Dholera smart city project is there, or gift city is there. So like if you want to monitor how that smart city projects are changing rapidly or not, or any infrastructure project if you want to measure. So for that we have to select very spatial, like spatial resolution will be very, like it will be too high, and temporal resolution annual scale will enough if we want to monitor the construction in the smart cities. Now on this right hand side you can see the different applications, so land use, land cover. So if our details are becoming finer, we have to increase our spatial resolution as well as our temporal resolution. So you can see here. Now forest cover mapping, we can go from 30 to 100, and then time will be 1 year. So if you go down from top to down, then this temporal resolution is increasing, and from right to left, this spatial resolution is increasing. So if you need very high resolution LULC map, which is categorized in different patches of the area, then you need very high spatial resolution, but not that high temporal resolution. Instead of that, if I see the all the natural disasters which are happening, let's say forest fire, flooding, landslides, earthquake. So for that, what is necessary is that if this phenomena will occur in the larger portion, like flooding will not happen at just one or two, for one or two building. It will happen in the a little bit wider area. Forest fire will also happen in wider area or wider reach. So 30 to 100-meter scale will work partially. But when we talk about temporal resolution, the temporal resolution for those applications when natural disasters are associated, the temporal resolution should be very high. It should be like 12-hour to daily scale temporal resolution we have to consider. And then we talk about when meteorological variables such as the temperature and precipitation during the, for measuring those phenomena, our coarser spatial resolution, if it is coarser, then it is fine. But the temporal resolution should be very high. Like if I want to say that whether flooding is going to happen in the next 2 or 3 hours or not, we need continuous data of temperature and precipitation, and based on that we will model floods in our using hydrological model or any model which can predict flood, and then that using that will give warnings. So if you want to go before that as well, so we need very high spatial temporal resolution, but the spatial resolution is coarser is also fine, because we need the general understanding of the how these meteorological variables are changing, and then based on that what is happening at the local scale or at the city scale or at the state level, that we are due to the flooding or landslide, that we are telling. So we have to increase our spatial resolution from this kilometer scale to meter scale, and then also like we can also decrease a bit temporal resolution as well depending on the type of natural disaster. Flooding is considered like humans are associated with that, so we need to prepare the response. So for that temporal resolution is high compared to the forest fire. So I think the concept of different resolution is clear to you now. So all the four resolutions, the spatial, temporal, spectral, and the radiometric. The spatial is representing what kind of object you want to resolve. The temporal is related to the how frequently you are taking the images of particular area. Then spectral is how sensitive your information you are getting from the imagery. If two similar type of two trees are there, are you able to differentiate between this or not? So for that I have to increase the spectral resolution. Then the third is like your spectral, and then your radiometric resolution, and then spectral, it means using the different spectral characteristics, how they will reflect under the electromagnetic spectrum. So how many bands you are considering. So is it clear now all the four resolutions and their applications, for which kind of application we can use it, for which resolution? Yes. By how? Okay, so temperature, it means the temperature is a property. We will not get the from the reflectance. Okay, so when we talk about reflectance, the energy is going to the object, it is reflecting and coming back. we will not get any type of temperature information from that. So if you want to measure temperature of any object, you have to use the property. There is three different property: reflection, emission, and scattering. So we have to use emission over here. So every object, according to black body radiation curve, they will absorb the radiation and then it will emit that radiation. Now that radiation which it is emitting, it is depending on like sigma t raised to 4, like whatever the energy is, Stephen Boltzmann law, it will absorb and then it will emit the energy according to the black body radiation curves. So now at what wavelength it is reflecting the energy. So it will be fall under the 3 to 10 micrometer region, which is like a thermal infrared region. So if you use that, then you can get the information about temperature. Now, when you are using emission as a source of energy, that you are like getting the emitted energy, the emitted energy will not be similar to the reflected energy. If I consider the same place, reflected energy will be more, but emitted energy will be less because of the emissivity of the different object is very different, and most of the object will absorb the heat and they will not emit like that much heat because absorption will not happen that much compared to the reflectance. So in that case, what will happen, that emittance is very less compared to the reflectance. So we have to consider some more area. Like from the, if we are taking a patch of 15 meter by 15 meter, the reflectance energy is fine, but the emittance energy is not that much that it can reach to the satellite. The energy which is being emitted from the object, it is not enough that it can go to the satellite, because it has to go through the atmosphere and their scattering and absorption will also happen, which will like sucks or absorb the each whatever the energy it is emitting. And that's why we have to consider a larger patch of the area. So when we are talking about the temperature applications, the pixel size will be coarser, or you can see the resolution of the satellites which are giving the temperature information, it will be coarser compared to the resolution of the satellites which are giving us the reflected energy. So principal, it is using the emission, and when we talk about the spatial resolution, then the satellite which is giving the temperature information, the spatial resolution will be less compared to the satellite which is giving the reflected energy. Is it clear? Okay. So is there any other question on this resolution part? Okay, if there is no question, now we will go to the color composite. So now when we talked about spectral resolution, then I have told you that we will get one image from for black blue color, one image for green color, one image for red color, one image for near infrared. But as a human, we can visualize this three different colors, which is RGB. If you open a paint and if you see the color, you can just represent any color using this three colors only, which is RGB and the different proportion of 8. So now from remote sensing, we are getting so many bands. So which band should we consider? Because just single image will look like just black and white image. That will not give us the proper idea. Because what is happening, like you are collecting the energy which is being reflected in the green band. So if that reflected energy is high in green band, then it will show the whiter patches, and if that energy is less, it will show the black patches. So basically whatever the energy we will get, that is in terms of black and white only. Okay. Now to make it the colorful image, what we have to do is we have to place it as a three different bands, as a band of RGB. So first what we will do, we will consider the blue band, and that we will place it as a blue, green as a green band, and red as a red band. So what will happen, that it will make a composite using three different bands, and that will look like vegetation will look green, water will look blue, snow will look white. So whatever colors we perceive as a human through our eyes, the same color we will see on the image. So what we are doing, we are taking blue, green and red band, and that we are placing as a blue, green, red. But now what about the rest of the bands? What about the near infrared band? you can see that near infrared band is quite reflecting more, and we want to get to we want to use that information to show it in our imagery, because cats and other animals can see visualize in this near infrared window, which is band number 5. And you can also see here that it is quite white compared to the blue, green and red. It means the energy which is being reflected in this near infrared band or band number 5 is quite high, and because of that we want to use that information. So what we will do is we will just change this thing to like this. So now we just shifted our bands a little bit up. Now whatever the green color band actually we have, that we will represent as a blue color, red as green color, and near infrared band as a red color. So we have just removed the blue band because it's too dark, and instead of it we use the near infrared band. So we just shifted this band to one step up. So now green as a blue, red as a green, and near infrared as a red. And whatever the image we will get after this, after mosaicing all these three image, we will see something like this, where you can see that most of it, like it is, the image is red. Overall, this image is red. So can anyone say like why this image is looking like red image? Yes. So reflectance value in the near infrared region is very high, and that we have represented as a red color. Because red color is having high value, we see the red colors in our image. So that is why our image is red. Now, wherever it is more red, then it is representing vegetation. And you can see water will absorb everything in this near infrared portion. So we will see blue and darker black colors wherever the water bodies are. And this is a volcano, so you can see some dust and the other thing over here as well. And see, this is white patches which you can see here. This is fragmented patches, that will be cloud. Like this we can interpret the different things if we compare the color composite. So what is our objective over here is we want to see the things which we are not able to see through our normal eyes or human eyes. We want to get the information what is happening in the near infrared, shortwave infrared, thermal infrared. So basically for that region we are collecting the near infrared band, and that we are putting as a red. So that is just color combination. So now what we will do is we will go to one particular site and we will see like different types of resolution and this color composite. So there is one site known as Sentinel Hub Earth Observation Browser. Sentinel Hub Earth Observation Browser. So I will present my screen. So you can see this kind of window, and if you want to download the data, you have to like log in, or like you have to make an account over here on this particular website, which is Sentinel Hub Earth Observation Browser, Sentinel Hub EO browser. So it is just I'm logging myself there. So once you will log in onto that particular site, you will see this kind of window where you can see map, and over here you can see the different features, the discover. So it will discover different data. Then visualize, it means how do you want to see it, which color composite. Then compare, it means you can compare the two different imagery. So first of all, here different satellites are given. So I request all of you also, because these informations are quite small. So I request everyone also to like just open this website in your device. I will try my best to zoom it, but still if it is not. So you can see under the Discover tab, the first option is data source. So if I click on Sentinel-1, it will show you the basic information about Sentinel-1. Then pixel spacing, it means the spatial resolution, which is 10 meter and 40 meter. Then revisit time, it means which kind of resolution. So revisit time means which kind of resolution. Yes, so how frequently that is covering the part. So higher the number of revisit, it means higher the temporal resolution. So it is less than 5 days using the both the satellite. And then there is data availability part. So since October 2014, the data are available, and then there's application for which purpose you can use this data. And here they have given two revisit time. So particular this particular mission has two different satellites. One is in ascending direction and one is in descending orbit. So if we combine the both the satellites, or then you can get the temporal resolution which is less than 3 days. Now we have the second data set, which is Sentinel-2. So for that you can see the spatial resolution is varying from 10 meter, 20 meter, 60 meter. So basically it gives the information at 10 meter. And then if bands like thermal bands are there, or bands which has very less energy, then we have to increase our pixel size, which is 60 meter. Now you can, if you want to see more information about this particular satellite, you can click over here, show more. And now if you go to that particular page, then it will guide us to the different types of bands which are available. So if you just go down, if you click on this Sentinel-2 mission, so it will show us what is the satellite that they have kept, at which time it is covering the equator. So how many satellites are there, payload, its description, then its orbit. So you can see this Sentinel-2 mission is orbit is sun synchronous, and this sun synchronous orbits are used to ensure that angle of sunlight upon the Earth's surface is consistently maintained. So now you can, if you this inclination angle, you can see this is sun synchronous, and this inclination angle is 98.62 degree. Then altitude of this satellite is 786 kilometer. Inclination is 98 degree. So inclination with respect to equator. So if we go down, so it has different bands now. So which band at which wavelength is given. Then it's temporal resolution, spatial resolution, spectral resolution, then radiometric resolution. So all those things is given here. Swath width means how much area it can cover in a one go. So 290 kilometer in one go it can cover. So you can see the spatial resolution of this satellite is 10 meter. So you can see this, if you take the entire electromagnetic spectrum, that how which of the bands are having 10 meter resolution. So this band number 2, band number 3, band number 4. See, these two are invisible, and then other one is the very near infrared. So these bands are having 10 meter resolution. So which is located at 490 meter, 560 meter, 665 nanometer, and 842 nanometer. Then 20 meter spatial resolution. So band number 5, 6, 7, 8A, 11, and 12. These bands are having the resolution at 20 meter. And then 60 meter, it means the blue, because in see that in blue the images were looking like very dark in color. So we need very good amount of energy. So to collect more energy, what we have to do is we just have to increase our pixel size or make it more coarser so that it can capture more energy to the satellite. So for band 1, band 9 and band 10. So what is happening over here is when the energy is coming from Earth to the satellite, atmosphere is there and will absorb the molecules present in the atmosphere, absorb all the energy. And that's why we have to increase the amount of energy which is going up. So how we can increase it? Like we just have to increase our pixel size. That is the only way. So that's why we have gone from 10 to 60 meter. Spectral resolution, you can see 4 bands in this RGB band and 1 in near infrared. Then 6 band out of for that 4 is in very near infrared region. 2 of them are in short-wave infrared, and then other 3 bands which mainly focus on cloud and atmospheric part. So that will be like for water vapor and other detection, that is at 60 meter resolution. So now you can see read about the different, like what is the reflectance radiance. So what is the value which is being radiated, and the unit is in watt per meter square per steradian per micrometer. So per wavelength how much energy is radiating back in the 3-dimensional. So this watt per meter square is from area, then this steradian is from, if we are considering the from volume how much energy is radiating, then this unit is for that, and then it is for specific wavelength how much is reflecting back. So that's why watt per meter square per steradian per micrometer. Then if we go down, it will be like for every band what is the wavelength and everything. So you can see now this graph you can see here. I will just make it big. So what it is showing is on the x-axis we have wavelength, and on the y-axis we have transmission. So how much like it can transmit through the atmosphere, or will it be absorbed? So over here you can see in this visible spectrum, most of the energy can transmit through that particular section. So wherever the energy can transmit through the atmosphere, we will place our band in those window only. Whereas you can see this particular window where you are not transmitting anything, because it means it is absorbing everything what is coming from the sun. It is absorbing everything in this particular wavelengths. So you can make this kind of curves for different objects, and then how much energy is coming, and then you can find out the spectral reflectance curve. So like this it will look like. So if you further go down, all the information about this particular satellite is given. So you can like click on any of the satellite and click on more, and then you can find out the different information in detail. What is all the 4 resolutions. Now we will see couple of more example. So this is a Sentinel-3 which is available from 2016 onwards. Then Sentinel-5P for that. So this is for measuring the atmospheric variables, atmospheric ozone monitoring, or SO2, or particulate matter, or radiations which are coming. So for that, I mean, we do not need that much spatial resolution. So you can see the resolution is 3.5 kilometer. And revisit time, like this how air quality is changing. So to understand that, we need very high frequency of monitoring. So you can see it is covering the 1 day. So revisit time is 1 day. So if I consider the Sentinel 1, 2 and 5P, so which satellite is having more highest temporal resolution? Sentinel 5P. Okay. Yes. So now what we can measure through Sentinel 5P, so carbon monoxide, nitrogen dioxide, ozone, and the other variables. Then this Landsat satellite is there. So for that you can see this is available from 1972. Spatial resolution is 68 meter, 83 meter, and then it is available for 18 days temporal resolution. Then Landsat 4 and 5, so which is available at 30 meter resolution, and revisit time is 16 days, and that is available for global regions, and from 1982. Now we see the current satellites, which is Landsat 8 and Landsat 9. So in that, if I will click on Landsat 8 and Landsat 9, You can see this partial resolution of one band, which is also 15 meter, which is a panchromatic band. And then revisit time of this particular satellite is 16 days. And this will be useful for vegetation monitoring, land use line curve map, and to monitor the changes. So like that, you can like click on each of the layer and you can find out their spatial resolution, temporal resolution, and if you want to get more details like spectral resolution, radiometric resolution, you just click on the link which is given in any particular data set and you just explore that. It will show you the different resolution, different characteristics of that uh, particular satellite mission. So that is all about resolutions. Now we will go to the next part. So let me share my screen. Just wait a second. I'm sharing this. Um, so are you able to see my screen?
Yes, sir.
Okay. So now the next thing we will see is like how this different objects will behave in different wavelength. So if I take any leaf or water and I will put the different types of wavelength on top of it. So how much it will reflect out of it? Will it reflect 100% or will it reflect 60%? Will it reflect 40%? So for each and every object, I will prepare some curves, which is known as a spectral signature curves. So now here you can see the example of green, which is vegetation. So from point 4 to point 5, which is blue region, it is not that much. When we go from point 5 to point 6, it is going up a bit. Why? Because vegetation will reflect more in green light. You can see here the first peak which is coming. Then it will stop like reflecting back because here is a red wavelength, zero point 0.6 to zero point 0.7. Now when we go to the near infrared region, more than 0.7 to zero point 0.1, it will reflect a lot of energy because of the chlorophyll content which is present in the vegetation, which will absorb the other light and reflect this particular energy, near infrared energy. So because of that, we will see the increase in the reflectance value in the near infrared region. Then as we go down, go forward, then over like 1.4 micrometer, you can see the absorption channels are there because of water present in the leaf and the vegetation. It will absorb the near infrared radiations which is coming, and because of that, there is a depletion in the reflectance value. So that's why it is going down, and then further it is going up, which is because of the microstructure of the leaf. Uh, so and then after further it is going down only. So by understanding the structure of any material or the object, we can put that under the spectral photometer, or the we can do the spectroscopy, and we can see like what is happening at the molecule level, which light it is emitting or reflecting more, and we can generate this kind of curve. Now we can see if I want to detect the vegetation from the satellite, I should use the spectral band which is around 0.7 to 1.2 micrometer. So if I want to differentiate between water and vegetation, so you can see initially in the blue wavelength, water is reflecting around 0.1% energy, 0.1 energy, which is around 10%. But as I'm going towards the higher wavelength, water is not reflecting at all. It's like around zero only. So if I want to differentiate between water and vegetation, the best band, possible bands is like after 0.7, I can use any band that will reflect water and vegetation well. So if I want to differentiate between any two different objects, I have to select my wavelength or bands in such a way that it should have high contrast between two objects. So you can see this darker gray color which you see in this image. So these are the bands of Landsat satellite. So one band in the blue region, then one in the green, one is in the near infrared, one in the so one in the red and one is in near infrared. Then one is around 1.6 meter. Then one is around thermal. So further you can see snow. So snow is having high reflectance in the till this portion of 1 micrometer. Then it is started depleting. Similarly, cloud also have a high reflectance till 1.4 micrometer and then it is going down. And if we see the dry grass, it is having less reflectance in the blue and green window. And then if we are increasing the wavelength, it is increasing with the wavelength till 1.4 micrometer and then it's gradually going down. So we can put different objects and we can see their spectral profile. So in specifically, if we talk about the vegetation, we see the leaves with the different colors like green, yellow, orange, or dark brown. So it depends on how much chlorophyll content present in the leaf. So if high leaf is having high chlorophyll content, it will reflect more green color. And then we can see the higher response in the near infrared region. Similarly, this absorptions which you see like the valleys are forming, so that is because of the atmospheric water absorption bands. So you can see that the absorption is too much which because of the water vapor present in the atmosphere as well as in the plant, and that's why we are not getting the proper reflected energy. And these two bands blue and red, we are not getting a proper reflectance because of the they are absorbing the chlorophyll will absorb those two bands blue and red and it will reflect the green. So why that's why this peak is coming near green but not near blue and red. So like that you can understand any object how it will reflect under different spectrum, and you can design your sensor at which wavelength you should design your sensor and what kind of object it should detect. And then you will do the same thing for n number of objects and then you will generate a spectral library. So now I will show you one spectral library which is available. So there is one site which will give you the spectral library of the different objects, which is known as a spectral characteristic viewer. So this is from USGS NASA, and you can just search for this spectral characteristics viewer in your browser. Spectral characteristics viewer. So how this tool is useful, that here they have kept different sensors and different objects. So you can see like what is the response of water in Landsat satellite, what is the response of water in the Sentinel satellite. So they have done the similar analysis using spectrophotometer and the same with the satellite, and they have compiled all the results over here. So you can just click on what kind of object you want to see, what kind of satellite mission you want to see. So currently my network is not that good so that I can show it to you, but you can explore this in detail further. So you will get to know more about uh, this particular viewer. So it will just have so many objects already inbuilt with it, like say different types of rock, different types of vegetation, different types of water. So the site name is Spectral Characteristic Viewer. Uh, I will search it on my screen. So I will search it one more time, or I will just put the link in the chat box. So you can go to this particular site and just check more into it. So it's from Landsat USGS Spectral Characteristic Viewer. You just note it down. I have just posted in the chat box. Okay. So now once we get the spectral signatures from different objects, now how to differentiate between different plants or different, let's say I want to classify my plants as a healthy plant or the dead plant. How to differentiate those two? So we have to use one feature. Let's say we will integrate more information so that it will create more contrast. So you can see here, if you take this different leaves, so at that leaf is drying, what is the thing that you can observe here is that as the leaf is drying, its response is decreasing in the near infrared window. You can see the green leaf and then you can see the brown leaf. So if you see the near infrared portion over here in this second box, in the top right corner, you can see the red box of near infrared window. So they are having this green and yellow leaf have more reflectance. But as the leaf is drying, their reflectance in the near infrared window is depleting. Whereas its reflectance in this red window is also depleting. So we can use both this information, which will create more contrast. So we will make some index, something like this: near infrared minus red, near infrared plus red. So what we are doing here is near infrared for this red is quite similar for most of the leaves, but this for near infrared they are showing significant difference between the two leaves. So we will use one band which is showing more difference and one band which is showing less difference, and then we will create some indices like this: near infrared minus red, near infrared plus red. So this is generally called as a normalized difference index. And then if this index is -1 to 0, it means there is no plant present there, or either the plant is dead. Then if it is between zero point 0 to 0.33, then it is an unhealthy plant. And then if it is from 0.33 to 0.66, it is moderately healthy plant. And then if it is greater than 0.66 to 1, then it is very healthy plant. So now we will just try to do that thing with the example, because it's not clear with the hypothetical examples. So what I will do, this is an image of Gandhinagar area near our campus, IIT Gandhinagar. And you can see here that I have marked out some of the pixels from the water and some pixels from the agriculture boundary. Now my task is I want to differentiate between water and vegetation. So for that, I will first plot the reflectance value for all the bands. So how much water is reflecting, how much vegetation is reflecting. Then after I can see that in the near infrared band, which is band number 8, the difference between water and vegetation is too high. And this red band, which is band 4, this difference is quite similar. So I can use those two bands in this formula. And if I will put both the value as NDVI, normalized difference vegetation index. For water, I will get the negative value. And for vegetation, I will get the very positive values. So now if I want to differentiate between water and vegetation, I can see if value is less than 0, it is water. If it is more than 1, it is just vegetation. Or more than 0, it's vegetation. Or more than 0.3 or some threshold I have to specify. So this is how it looks like, that particular site looks like in the true color composite. So I think my screen is taking time to load. Yes, yeah, that's it. So this is the how that image looks like in a normal true color composite. If I take using the satellite, if I present red as a red, green as a green, blue as a blue, it will look like this. So you can see some green patches of vegetation, some water is also present in this river, and then some buildings are also there in this Gandhinagar cities. Now I will find out the NDVI for first of all, this is the false color composite image. So false color composite image, you can see now this water is become very like water and vegetation you can differentiate easily, because water is totally absorbing the energy, whereas in near infrared, whereas vegetation is reflecting. So now after that, I will find out the NDVI. So NDVI, I will represent it as a, like, now you can see more the green color, it means higher the vegetation, and less than 0 I made it to blue color. So it means whatever less than 0, it's showing water. So I can differentiate between water and vegetation like this, and then I can clip my images for this particular Gandhinagar area, and if I represent how it is changing over the time, I can make this kind of animations that over the year how this NDY value is changing. So during after monsoon it is becoming green, and then after it is becoming dry during the summer season. So it will reflect the patterns. So like that, this is just for sub-district analysis, and then you went to Gujarat level analysis. So this data is from Modi's image. So now you can compare this 250-meter data set will not like it's not representing information. You can see clearly if you are taking the state level information that which part of the states are becoming greener, which part of the states are becoming drier. Similarly, for India, if you want to take, Modi's is a good data set. And then they are having their limitations, and every index their limitations. So how to improve those limitations? This index is not capturing the information about the soil property, because we are getting the reflectance from soil also, which is present near to the plant. So by removing that, we can increase the. So similarly, now if I map this thing for entire Brazil, then how it will look like. So I have found out the forest laws from one of the portal. I have taken this data sets, and you can find out that how the forest is changing from the 2001 to 2018, which area got reduction in the more forest loss and something like that. So you can map this kind of animations afterward. Similarly, this next slide is showing the effect of agriculture. So how the agriculture is impacting the forest land, and how the urbanization is taking place along the road which is passing in the Brazil, which is BR-163 highway. And then how on the right hand side you can see the images from forest fire, that how the actual image from forest fire will look like from the satellite remote sensing. So this is forest fire that they are putting for the this making the agriculture. So one example is the urbanization, and one example is the for pasture land they are making the new forest. They are just deforesting it, and they are taking a crop there, which is known as a zoom cultivation as well. Then if you plot this thing on a map, then you can see that how this will look like. If you just zip it and just put it, you can see that how some area got changed in the last 10 years, and then what is the reason behind it, whether it is agriculture or some other reason which is responsible for the urbanization forest loss. So similarly, now the next topic is the forest fire monitoring. So there we will use this winds displacement law, which will tell us that if the temperature of some object is this much, it will radiate the dominant wavelength in that particular wavelength. The formula of the same is 2898 by T, where the T is in Kelvin. And when we talk about forest fire, the normal temperature is from 500 to 1000 Kelvin. So if we plug this thing into this equation, it will become this 3 micrometer to 5 micrometer. The wavelength it makes, it can emit the energy, which is falling over here in this electromagnetic spectrum, which is our thermal infrared region. And this is the bands which is available in the MODIS. So the bands which has 1, 2, 7, 21, 22, 31 and 32, and what is their purpose? So for which purpose we are using those bands? So MODIS has having 36 spectral bands inside it. And then this is like a Forest Survey of India, what they are using as a forest fire monitoring. So if once you get the temperature, so if the temperature is greater than 310 Kelvin, and the difference between the pre and post imagery, if that is greater than 10 Kelvin, or band number 86, or the wavelength in the 86.86 micrometer, if that value is less than 0.3, then that pixel is considered as a fire pixel. So these three conditions should follow, that temperature should greater than 310 Kelvin. The difference between this fourth band and 11th band is should be greater than 10 Kelvin, and then wavelength of 0.86 micrometer band should be less than 0.3. So whatever the reflectance which we are getting out of it. And if it is during night time, then just one condition that T4 threshold should reduce to the 30 So we'll remove everything because during night time there is no reflectivity. So we'll just consider the band number 4, and then this if that value is greater than 305 Kelvin, then it is considered as a fire pixel. And then it can be like according to your spatial resolution, you can put where the fire is happening. So if the fire is happening in this pixel, it will give you this pixel. Then if you increase your fire, like if your fire is happening covering all the 4 pixels, then all the 4 pixels will be classified as a fire pixels. So like this, people will use this methodology and they will map the particular areas which are the fire prone or the where fire occurred and then burning. So this thing you can monitor, and once you have all the data sets, you can put various data sets into GIS platforms such as QGIS or ArcGIS, the similar software which I showed in the last class, and then you can use it for various applications. You can put the human settlement layer, you can also put the roadway network, canal network, railway network, and then how flood affected the railways, how flood affected the road network, and you can answer those kind of questions after putting each and every data set. Now we will see some of the questions and answers. So the first question which we have, like spectral signature of an object. Spectral signature means how it is responding in the different wavelength with the curve which we show. It does not depend on which parameter. The spectral signature of object. Yeah. Abhi, do you want to say the answer? So what will be the correct answer according to, can you able to guess it? Season, wavelength, SWAT, or reflectance value from the object? So I think the answer will be SWAT width. Why? Because season of the year. See, if you are monitoring vegetation, if you take pre-monsoon imagery and post-monsoon imagery, it will change the spectral signature as we see in the different leaves. It is going from green to yellowish or reddish. So season will make a change in the spectral signature. Wavelength, if we see in the red portion or thermal infrared portion or some other portion, the reflectance will be different. So that option is also like it will also change spectral signature will change with the wavelength. Then reflectance value from the object. If reflectance is more, then spectral signature is high. So that is like this is common sense. And the swath width is means how much area it is covering. So if it will cover more area or less area, how much it is reflecting, it will not affect on that. It will affect on spatial resolution, spectral and temporal resolution, but not on the how much area it is covering. Whether it is covering less area or high area, it will not change the characteristic of the object. So the correct answer will be the C, that spectral signature does not depend on the SWAT width. Now these thermal infrared images are provided by which satellite missions? So if you see explore the portals like Sentinel, EO Hub and so on and so forth, you will get to know that this Landsat TM and this NOAA IVHHR sensors are providing thermal infrared imagery, which we are using this means displacement law, and they are finding out the temperature, brightness, temperature. So this you should know the different products which are available in the market. Now we have a topographic map prepared by Survey of India, which covers 1 degree by 1 degree area on a single map. The minimum ground distance which can be presented on this map is filling the blank meter. So this is like related to this spatial resolution. So this is more kind of application part. So first of all, we have to understand that how Survey of India prepares the map. So basically, Survey of India gives this kind of topographic map. The first map, which you can see the entire India map, and you can see the numbers on it, like 32, 35, 36, 37, like the bigger tiles which you can see. That is known as a million sheets, which is representing the area of 4 degree by 4 degree. And the corresponding scale for that is 1 raised to like million. and that is represented by in code, in terms of code, it is represented by 4352 like that. Now then we go to the next one, which is like we are going towards the 1 raised to next scale is 53C. So whatever the box which we are able to see earlier, we will divide that box like it was earlier 4 by 4 degree by 4 degree. So now we will make it to 1 degree by 1 degree. So we will divide it by 4. So number of pixels will be increased by from 1 pixel to 16 pixels. So it will number of pixels will increase by 16 times. And then the corresponding scale will change to 1 inch is equal to 4 mile, and in terms of scale it will become 1 is to 2 lakh 50,000. Similarly, as we go down, the scale will change, and then we have to see for 1 degree by 1 degree grid, what is the scale, which is 1 centimeter is equal to 2.5 kilometer. So then you can convert that 1 centimeter on map is represented by 2.5 kilometer on map, and then you can convert that into how much ground distance we can observe. So you just have to remember the scales which Survey of India is giving to us to solve this kind of questions. There is one more question. Are you able to see my screen? Please repeat the question number 29. Okay. So the earlier question was like topographic map was given, which is 1 degree by 1 degree. So what is a minimum ground distance which we can represent it? So first of all, you should know when we talk about 1 degree by 1 degree map, which is given by Survey of India, what is the scale associated with it? So the scale which is associated with 1 degree by 1 degree map, which you can see in this table, is 1 centimeter is equal to 1 centimeter on map is representing 2.5 kilometer on ground. So you just have to convert that into meter first, and then you can just put that as an answer. The main thing which you have to understand over here is how Survey of India is indexing the different maps. The first is a map with a very low scale is 1 raised to million, which is we are representing as a grid of 4 degree by 4 degree, which is at a scale of 1 centimeter is equal to 10 kilometer. Then we will divide that grid into further parts by 4 by 4 degree to 1 by 1 degree, which will become 16 number of divisions. Then when we talk about this different topo sheets, then you can see if the topo sheet number is 53C8, it means that 53, you first have to locate the 53 number of this square. Then in 53, there is a subdivision from A to P. So you have to locate A, B, C, D, E, F, G, H. So you locate C. And once you have C, you will have something like this, which is presented below. So first, let's say we will have 55, which is over here. Then C, so 55C, and then or 55D, so 55D, and then in D, let's say 11 is there. So 55D11. So that is a way of numbering that Survey of India follows to if you want to find out any particular topo sheet maps. So how these maps will look like, you just go to the Survey of India sheet and then just write Survey of India topo sheet, and you will able to see different this kind of maps, and I will probably show this kind of thing in the next lab as well. So that's it. You just have to remember the what scale, which degree, and what is the corresponding scale. Then the next question is like how many number of cells a 30 meter spatial resolution DM would be required to cover the 1 raised to 50,000 topographic map. Now first thing, like if Survey of India map is having scale of 1 raised to 50,000, what is the area that it can cover? So in the earlier slide we show that if the scale is 1 raised to 50,000, it will giving 15 minutes by 15 minute. One map will cover the area of 15 minute by 15 minute. Now 1 minute is 1.85 kilometer. So what will be the 15 minutes? So 15 minutes will become 27.75 kilometer. So our map can cover at one side 27.75 kilometer. Now we have to see how many pixels it can accommodate if the size of the pixel is 30 meter. So what we will do, we will just do the 27.75 into 1000 to make it into meter, and then we will divide it by 30. So it will give us the total number of pixel in one line. And now image will have to length and width, so we'll multiply that number. So 27.75 into 1000 into 27.75 length and width, and then pixel size is 30 by 30. So we'll get our answer as 855,625. So if we are using a map of 1:50,000 and we are presenting that with the 30 meter spatial resolution DEM or image, then it will consist 8,55,625 pixels inside it. Is this clear?
Yes, sir.
So only information which you have to remember over here is that if Survey of India map is 1:50,000, how much area it can cover? So it can cover area of 15 by 15 minutes. So that thing is not already given. You just have to infer by your understanding or your experience.
1 minute is equal to 1.85 kilometer. 1 degree is equal to 111 kilometers.
Yes. So 1 degree is approximately 111 kilometer. At equator, that is also we have to specify at equator, because if we are going at pole it will change. So now the next question is choose the correct statement. So this is about the color composite which we have like represented, just true color and false color. One is red and one is green, which we showed earlier. So can you try to, do you want to answer it? So the first statement is true color composite is produced by superimposing red bands as a red, green as a green, blue as a blue. So that statement is true. Now the next one is true color composite is produced by blue in red, green with green, and red in blue. So that is wrong. The earlier one is correct. Now the two statement are yes. Yes. So now we see the statement number C, which is standard false color composite is produced by superimposing near infrared with red, red with green, and green with blue. So we have removed the blue colors. So this is right, and the next one is wrong. So option A and C is the correct statement for true color composite and false color composite. So option A and option C are correct. Then we have the next question. Then when we do the visual inspection of the satellite images, so which parameter is the primary and which is the secondary? So yes, yes. So tone and color is the primary, size, shape, and textures are the secondary. Then option A, this is a multiple choice, so more than one is correct. Then the option C, which you can see, the texture refers to the frequency of the tonal changes in the area of image. It means we have seen the grass and forest. So there is a tonal change. Where is one is smooth, one is a some variations were there. So option C is also correct. Then we have the next question, which is we have two images. One is image P and one is image Q. Image P is 80 meter having 80 meter spatial resolution, and Q is having 20 meter spatial resolution. And both are having 512 by 512 pixel. So for this two image, which statement is a correct one?
Option B is correct.
So,
Option B is also correct.
So option B, P will cover 16 times more area because resolution is coarser, so it can cover more area. and image P is higher. Option P is higher resolution. So that is wrong. Why wrong? Because option D, see, P is higher resolution. Higher resolution means what? It can distinguish between two features. So one is 80 meter, one is 20 meter. So which will give more information, P or Q? So you have one image with 80 meter resolution and one image with 20 meter resolution. So which one will give more information to you, 80 meter or 20 meter? Okay, so what I'm saying is you have two image, one with 80 meter and one is 20 meter. So which one will give more information as we see in the PEDI example? Yes, sir, 20 meters. Sorry, sir. Exactly. So option B and C will be correct. That minor details will be more clear in image Q, which is 20 meter as compared to the image P. Okay. Is it clear? Yeah. So just keep in mind, higher the number, it doesn't mean the higher the spatial resolution. Lower the number, higher the spatial resolution. 1 meter is high spatial resolution compared to 100 meter. So here option A and option B and option C is correct one. Now the next question is hyperspectral images. So hyperspectral images is means how many spectral bands we have. So if we have more number of spectral bands, the number of bands are more, then it is considered as a hyperspectral. And if number of bands are more and it is continuous, and the bandwidth will be narrow. So in RGB we are having just three bands. One is R, one is G, one is B. But instead of it, we have more number of bands. Like we are representing all the 7 colors of rainbow. Then it will be like become hyperspectral. So basically in hyperspectral we have more than 100 or 325 bands also. So bands are more, bands are narrow, and bands are continuous. The next thing is number of cells required to cover an area of 9 square kilometer of ester GDMR. So here they have directly given the uh, satellite mission, which is ester GDM. So first thing you should know that what is the spatial resolution of that satellite. So basically this ester GDM satellite is giving the data as 30 meter by 30 meter resolution. So if I tell you that it is having 30 by 30, then find out that how much area, how many pixels are required if we want to cover 9 square kilometer area. So what we will do, just 9 square kilometer will convert into meter square, and then we will divide it by 30 by 30. So 9 will just convert from square kilometer to meter, and then divide by 30 meter by 30 meter, because pixel resolution of ester GDM is 30 by 30. If I ask you here Sentinel, then Sentinel 2 is 10 by 10 meter, Landsat is 30 by 30 meter. So you should remember the spatial resolution of famous satellite missions, which is like Sentinel, Landsat, Ester, SRTM. So these are the common satellite missions. If you talk about ISRO, then we have Research, then LIS-3. Then now the next question is like to visually distinguish between river channel and canal. You have two different things, river and canal, and you want to differentiate between these two. So which parameter will be useful to you? Size, shape, tone or texture? Exactly, because yeah, shape will be the factor, because the size might be similar also, but shape, like canal if you take, it has like smooth lines, whereas river have like just channels, like which is zigzag pattern. So the correct option will here be shape. Size might be same also for some rivers and canals, but shape will not be similar. Now the ratio between the so what I'm saying is the shape will be main parameter. Size will be like similar also for canal and rivers. Both have similar width also, different like similar size as well. But their shape will be different because canal is like more linear feature, whereas river is more zigzag pattern. Is that clear? Uh, is that clear? The differentiation between river and canal? Yes. So now the next question is, what will be the ratio between the, so the next question I will just repeat. I think my laptop got turned out automatically. So what is the ratio between the reflected energy to the surface energy, which is incident energy? It is known as a. So when we are talking as a ratio, what is whatever is coming and then whatever is going out. So that ratio is known as a what? So energy which is reflecting back divided by energy which is coming in. So that is known as a, so the energy which is reflecting back divided by the energy which is incident. So that is known as a reflectance. What is going back from whatever came. So that is known as a spectral reflectance. And when we talk about the unit of it, then it will be termed as we seen in that particular site, that unit of spectral reflectance will be watt per meter square per steradian per wavelength. So it will be micrometer. So now that is two different questions on the reflectance. Uh, then we have a couple more questions, but I think you are not able to see my screen. Yes, yeah, I'm having just poor connection, so that's why it's. So I think what we can do is we can cover the rest of the questions in the next, probably like in the next lab. My next network is fluctuating a lot. So I think what we can do is we can try to cover all the questions from the beginning. So is it fine, Abid? So we will, yeah, we will revisit all the questions in the next class, or if that doesn't allow as per this schedule. So what I will do, I will record a better video with all these questions, and I will post it on YouTube. So like whatever is feasible from the NPTEL side, I will try to do that. Okay. Sure, sure. In study, yeah. Previous slide, is it not there? Okay, so today's slide I will upload there. I will upload it by tomorrow. Sure. Chalo. Then in that case, we'll just close this meeting. See you and goodbye. We'll try to solve it in the next week. Yeah, good night.